Hello everyone, this is G for Test 1 Core Logging done by Group 13. Introduction. The characteristic of a rock which play a major role in determining its engineering properties and need to be given due attention when describing the rock are the strength, weathering effects, and discontinuities. And the discontinuities are the most significant of these. Core logging is important when rock material is required for construction purposes. The objective of this test is to obtain physical description and RQD of rock cores recovered from borehole drilling.
For core logging test, the apparatus that we use is rock samples or core samples, which is approximately 1.5 meter, a core barrel, and a measuring tape or a long ruler. The methodology is, first, we look for the weathering state or special features of the sample and state in table 1. Look for any decolorization or chemical spots or natural signs. As an example, fractured lines as in the core samples are shown. Then, we measure the length of the core samples in sections. Each sections are divided by the fractured lines. Note that there may be some of the sample that are unable to be recovered, but we still arrange the core samples according to its original excavation length in the core barrel. Then, we will record all length obtained from the core sample measuring process. And then we will calculate the core sample recovery by sum up all the length of the core samples obtained using the formula core recovery, which is total length of core recovered divided by the total core length, which is 1.5 meter times 100%. So we will get in a percentage form. And then we will calculate RQD using every length that are more than 100 millimeter using the formula given, which is the total length of sound piece, which is more than 100 millimeter, divided by the total core length, which is 1.5 meter times its 100%. So we will get in a percentage form. Okay, the last step is repeat all the steps with core sample 2 and 3.
For the data calculation, we are given a sample recovered from borehole and excavation. Firstly, we have to measure the length of core it recovered and the length of core in pieces with greater than 100 millimeter. For the calculation, the core recovery CR is given by the formula length of core recovered divided of length of core run multiplied with 100%. And for the rock quality designation RQD, the formula is length of core in pieces greater than 100 millimeter divided of length of core barrier multiplied with 100%. In the result, we calculate that C1 with the CR 93.33% and the RQD is 86.67%. For the core number 2, the CR value is 98.67% and the RQD value is 74.67%. Lastly, for the core number 3, the CR value is 64% and the RQD is 56.67%.
As for the conclusion, we found out that the core is through a discussion with the technician, and based on the table, as you can see here, from 0 to 25% RDQ quality resignation, we have very poor rock quality. From 25 to 50%, we have a poor quality. From 50 to 75%, we have a fair quality. From 75 to 90%, we have a good quality. And from 90 to 100%, we have an excellent rock quality. So we have found out that that C1 is a good quality rock, and both C2 and C3 are fair quality rocks, which have an RQD of 86.67%, 74.67%, and 56.67% respectively.
Hello, I will explain about Lab G4 for the second test, which is Schmidt Rebound Hardness test. So, what is Schmidt Rebound Hardness test? Schmidt Rebound Hardness test is a test done to determine the rebound strength of certain body of sample material, particularly rocks, using a Schmidt's hammer. This test is widely used in engineering field and is commonly to determine the strength of a structured body. What is the usage of Schmidt's hammer rebound hardness test? The Schmidt's hammer rebound hardness value, which is R, is perhaps the most frequently used index in rock mechanics practice for estimating the uniaxial compressive strength, which is UCS, and the modulus of elasticity, which is E, of intact rock both in laboratory conditions and in situ. The Schmidt's hammer is also widely used for estimating the UCS of discontinuity walls and assessing the workability, excavability, and borability of rocks by mechanical means such as cutting, milling, and etc. So this is how a Schmidt's hammer works. For a loaded state, the upper spring is fully compressed and the lower spring is extended, and the indicator will lock at 0. So after firing, the upper spring is still fully compressed while the lower spring will be at rest. So the indicator will show or reads the momentum rebound, and when it is in ready to fire state, both springs slightly compressed and the indicator will lock at 0, which is it does not read anything.
The apparatus needed an empty plastic cup with straw as Schmidt hammer, plastic box as steel base, cylindrical speaker as cylindrical rock specimen, and mouse pad as sandpaper. Okay, first what we need to do is to make sure that the rock specimen is free of dust and clean with sandpaper. Then we place the steel base on a flat and level surface, and we put the rock specimen into the steel base to prevent vibration and movement. Next, we take the Schmidt hammer and place it perpendicular to the surface of the rock specimen. Then we press the Schmidt hammer gradually against the rock specimen surface and we press the button on the Schmidt hammer to lock it, and then we can read the reading. Remove the plunger and record the readings observed. Then we repeat the experiment on a different position to get the average value.
For the data calculation, we are given the graph of average depression of strength for most rock versus the strength hardness of hammer. In our experiment, we are given the rock is granite with the rock density 26 kN per meter cube, and the first rebound value is 43 and the UCS value is 97. For the second rebound value is 35, we are given the UCS value is 65, and the third 32, UCS value is 55, and the fourth rebound value is 30 and the UCS value is 49, and next 48 with the UCS value 134. Next rebound value is 36 with the UCS value 68, and the next value is 44 with the UCS value 100, and the last two value is 40 and 32 with the UCS value 82 and 55. Next, we have to calculate the average rebound value, and the equation is given summation of rebound value divided with the total number of reading, and we calculate that is 37.78 for the average rebound value. Next, we have to calculate the average UCS value, and given the formula summation of value of UCS divided of total number of reading, and we calculate that the average UCS value is 77.28 SEAA2012.
Schmidt hammer is used to estimate the strength of the rock specimen and for comparative investigation. The higher the rebound number indicates the stronger the rock is. From the experiment, the density of the rock is 26 kN per meter cubed and the average rebound number is 37.78, while the average UCS value of the rock is 77.22 Newton per millimeter square. Since the UCS value is indicated between the values of 50 and 100 Newton per millimeter square, according to the ISRM standards, the rock is strong and it has low-grade metamorphic rocks, marbles, some strongly cemented sedimentary rocks, some weathered and metamorphic igneous rock.